Um, so the title has two parts, Lefschetz fibrations and closed exotic four manifolds. So I'm the closed exotic, Zoltán will be the Lefschetz. So what is the motivating problem? Let me just start with that. I should also say that some part of my lectures has been delivered just 40 minutes ago. So I was planning to talk about Cyber-Witten invariants, so it will be short. Okay, so the objects we are considering are X, closed, connected, oriented, four manifolds. Well, we know what four manifolds are. These are topological spaces which we assume to be compact and no boundary, connected, and so these are just locally like R4. And so I didn't specify whether it's smooth or topological, so let's assume that these are topological four manifolds, i.e. Every point has a neighborhood homeo to R4. So that's the definition. And the question, the motivating question is, which topological manifolds admit a smooth structure, which just means that we take sort of a subset of these local charts so that the transition functions are differentiable as opposed to just continuous. And if they do, how many different they do. And the fact is, facts. So X compact, so it can admit at most countably many smooth structures. If the dimension is less than or equal to 3, then this problem has been solved, and every topological manifold of this type, closed, connected, oriented, and so on, admits a unique smooth structure. And in fact, it's a very important property of, say, three manifolds, because this is sort of the starting point of the solution of the Poincare conjecture. You have a topological three manifold which is simply connected. You equip it with a smooth structure. You run some complicated PDE, and then you read Perelman's papers. You try to understand, and it's a long story. And at the end, you get a classification. So, but it's a very important tool that you can apply very high-level analysis in understanding topology. Okay, what happens if the dimension is at least 5? Then there are always the number of smooth structures up to diffeomorphism is always finite. Finite, including the possibility to have 0. And then in dimension 4, so maybe I will continue here. If the dimension is 4, then there are examples with no smooth structure, with infinitely many, and by this principle, it's accountably infinitely many distinct smooth structures. And further facts that no known example of finitely many, but this finite number is bigger than 0. So we do not have an example of a four manifold for which we would know that it has 17 different smooth structures, but not more than 17. Okay. So okay, and one other fact that the question is open for, and now I will list the the simplest four manifolds. This is a very sort of upsetting list. So we have no idea what happens for S4. This is the famous single open question among these generalized Poincare conjectures. We don't know the answer for CP2. This is, you can imagine that S4 is like the one-point compactification of R4. This is sort of the complex algebraic compactification of C2. We don't know the answer for probably the simplest four manifold. This is just the product of four one-dimensional manifolds. Indeed, we don't know the answer for S2 cross S2, or more generally, for the product of two Riemann surfaces. So these are the manifolds you build naturally out of smaller dimensional manifolds. As it will turn out, if you build your manifold in a more complicated way out of smaller dimensional manifolds, like the way Lefschetz fibrations will be explained, then you will have a lot of examples, and all will fall into the category that they have infinite, not all, most of them will fall into the category that they have infinite many smooth structures. Okay, so I just wanted to add this line that there is plenty to do. So, take it on you. All right, so how do we understand the topology of a four manifold? So the most important, this is the eraser, right? Yeah, okay. I mean, if somebody left something here. Okay, so S1, no. Okay, so, let me disappoint you. There is an infinite list here. This is already infinite, but there is a lot of four manifolds we don't know. As you will see, I will add to this list more and more. So what's the first question? So you see a four manifold. What do you do? So the first, most important invariant is the fundamental group. This is always a finitely presented group, finitely many generators, finitely many relations. And the bad news is that any finitely presented group can be the fundamental group of a smooth, oriented, closed four manifold. So this brings in all kinds of complications, and this also brings in this idea of focusing on some subsets of four manifolds where the pi1 is sort of tame. For example, pi1 is trivial, or finite cyclic, or things like that. So that's the first thing. The next is you take homology groups, and by Poincare duality, you can, of course, take cohomologies. Remember that we are always considering oriented four manifolds, so this means that we have a fixed generator of the fourth cohomology, which is just isomorphic to the integers, and we just pick one generator. Okay, so these are isomorphic as groups. If we assume, for simplicity, that, say, the manifold is simply connected, then there is very little remained from the homologies. The zeroth and the fourth are always isomorphic to Z. The first and the third, if we have simple connectivity, are gone, and there is the second homology. So, and this turns out to be a free group, so you can characterize with one number. This is what I will always denote by B2, is the rank of this group. Okay, but we know that homologies are nice and very geometric, and we learn it in school. Cohomologies are a little better because they come with a ring structure. So we have this form Qx, which is defined on the second cohomology, which is just equal to H4 xz by taking two elements and sending them to the cup square. Or if we would like to be absolutely pedantic, we can say that we just send it to the evaluation on the fundamental class, which is just given by the orientation. So this turns out to be, so this is called the intersection form. And this is a symmetric bilinear and unimodular So it's clear what symmetric means. You just flip the order. Bilinear is obvious. Unimodular means that if you pick a basis in this free abelian group and you write down this QX in a matrix form, then the determinant of that matrix is plus or minus 1, meaning that it's invertible over the integers. And these objects have been studied for quite some time from number theory, and here are further facts. I'm sure that this is known for most of you, but maybe not all. And I will not make a poll that like everybody knows this stuff, because then, you know, you just watch it like a good movie, like Casablanca or something. Okay, so what are these? So fact. If QX is indefinite, so there are elements which have positive and there are other elements which have negative squares, then in an appropriate basis, it looks like some number of the 1 by 1 matrix containing a single 1 and some other number minus 1. Yeah, this is not what I wanted to say. This is characterized by 3 numbers, quantities, which is the rank, the signature, and we know that over the reals. So notice that this is over the integers. Over the reals, every symmetric bilinear form can be diagonalized. We learned that as Sylvester's theorem, and then it is determined how many plus ones and minus ones and potential zeros we have in the diagonal. The zeros are excluded because we have unimodularity, so it's a non-singular form. And the number of plus ones and minus ones are denoted usually by B2 plus and B2 minus, and this is just the difference between the two. This is the sum of the two, and there is a 0 or 1 type of property. It's called a parity. It's either even or odd, as parities are usually do. But if QX is definite, then it's complicated. The usual sentence which I say, and I don't think I ever checked, that say if you take rank 40 definite symmetric bilinear unimodular forms, then there are more than 10 to the 80 of them, which is like, I don't know, the atoms of the universe, or, you know, it's like a gigantic number. Luckily, it turns out that we don't have to worry about those forms by Donaldson's diagonalizability theorem, which I will refer to a little later. But no, I will refer it right now. So theorem. So Donaldson. If X is smooth and QX definite, then QX is, in an appropriate basis, can be represented by the identity matrix, well, plus or minus, depending whether it's positive definite or negative definite. So you have this gigantic zoo of definite bilinear forms, but basically none of them appears. There are only 2, the trivial all ones and the trivial all minus ones will appear as intersection form of smooth manifolds. So if you are interested in smooth topology, these are the only 2. And there is the theorem of Friedman saying that, so how did I phrase this? So suppose x1, x2 smooth four manifolds. So with all the adjectives of connected, oriented, compact, and so on, and pi 1 of xi1. So we are considering trivial fundamental group, and I'm sorry, I will just continue here. Then x1 and x2 are homeomorphic if and only if these intersection forms coincide or equivalent, which happens if and only if they have the same rank, or maybe I will just phrase it with Euler characteristics. So Friedmann's theorem tells you that the smooth four manifolds are homeomorphic. Notice this category change. So we don't have a condition for these smooth manifolds to be diffeomorphic, but they are homeomorphic if and only if, and there is a sort of a nicely checkable list of conditions. If they have the same Euler characteristics, this is the signature. And then there is this mod 2 invariant parity of the intersection form. So this gives us a sort of hands-on tool to determine whether two four manifolds we constructed using smooth constructions, whether they are homeomorphic or not. We have to check these algebraic topological quantities, and if they remain if they turn out to be the same, then they are homeomorphic. That's fantastic. And so in order to produce more and more of these exotic structures, we need several constructions, and this is what I would like to focus on. We need tools to show that these constructions give the same topological four manifold, so they are homeomorphic. This will be always the tool, Friedmann's theorem. I should mention that, because we are talking about smooth four manifolds, in this version of the theorem, Donaldson's result is incorporated. So this is why I kept this order. Say it again. I have my phone here. Shall I put? Maybe, I see. How about we put it on, what's the name of this? Airplane mode? Does that help? Do the same, then we'll see. Is it better? Okay, and I don't move. Okay, so we have we need the constructions. I will talk about constructions. We need a way to determine whether the results are homeomorphic. We have Friedmann's theorem, and now we need a tool to distinguish them, to show that smoothly they are not the same, and this is how we generate more and more exotica, hopefully infinitely many. I should add that, in an optimal world, we would generate an infinite list which contains all examples of that homeomorphism type, and we have no hope to doing that at the moment. Okay, so need diffeomorphism invariance. So I was hesitating what to do. In my original notes, I was thinking of introducing Seiberg-Witten invariance, but that just happened an hour ago. So I will just rather cheat, and I will sort of refer to that. So we learned very quickly what the Seiberg-Witten equations are, and I will just write those down. So we have, so what was the symbols? So we take a connection, so XS spin C four-manifold. So S is the spin C structure. We just choose one. It turns out that every four-manifold has a spin C structure. Every oriented four-manifold has a spin C structure. And we take L is the determinant line bundle. And there were the two U2 bundles. They were S plus and S minus, probably. S plus minus, the two spinor bundles. And then we consider solutions of these equations so a connection on L, so it's a U1 connection on the determinant line bundle, and psi section of S plus. The form of the equations at this moment is not so important. I should point out that, you could try any PDE. I mean, how would you distinguish two smooth objects? You say that I associate to some natural PDEs to both, and then I check how many solutions these equations have, and if the set of smooth functions are different, then I hope to identify a set of equations which distinguishes them, which provide different number of solutions. This is a risky project, because what can happen is that you come up with this fantastic PDE, and then the solution set, for some stupid reason, becomes topological, like the D operator, the exterior differentiation. We know from the RAM theory that that will not give you anything beyond topology. Or, on the other extreme, in order to set up the equations, you need a Riemannian metric, and you are so unlucky that the solution set will depend on not only the smooth structure of the manifold, but the Riemannian structure. So to find the balance is a hard game, and this has been discovered by Donaldson in the early 80s, that the self-dual part of the curvature of the connection might be a good choice for that. He did it in a different context. The connections were living on another bundle. But this is sort of the most important part, this plus. We take some part of the curvature, and this only happens in dimension 4. So you have to appreciate that plus, and I hope in the discussion session you will see how this plus is defined and why is it so important. But nevertheless, we just take the solutions path. So consider the solutions. The bad news is that if you have one solution, then you have too many, because there are symmetries of these equations. So there is this gauge group, G, which is just smooth maps from the manifold to S1. And it turns out that they act on these pairs. I will not write down how, but it happens that they transform solution to solution. So we just take the quotient, we would like to understand the really different solutions. So let's take M to be the space of solutions mod gauge. Well, it turns out that after a lot of work, this is a compact, smooth manifold. There's a little cheating here, I will explain, which is oriented and of dimension D, and here a familiar formula is coming. And I'm not sure it's readable. So D is 1/4 the first Chern class squared of the spin C structure, minus 3 times the signature of the manifold, minus 2 times the Euler characteristic. So this is a number. You know, it's 1/4. So again, you need a little bit of conviction that, you know, you believe that it's an integer as a dimension, but it is. And so when I say smooth manifold, it might not be true on the nose, but if you pick your metric generically and you modify the equation a little bit, you add the perturbation term in the second equation, then it will become a theorem. And in order to have an orientation, you have to fix some extra on the manifold. It's called a homological orientation. It's something on the cohomology. So this is a very mild extra piece of information, and you get this. So this is fantastic. So what do we do with that? I mean, we get a potentially a very high dimensional topological manifold. So what do we do that? It turns out that this sits inside the configuration space which is just you take all the pairs without satisfying this equation mod gauge, and this is a much bigger space, and it turns out to be that it is homotopy equivalent to CP infinity. And this is a good news, because we know the homology of CP infinity. So we have a subspace which is a compact oriented manifold, so it has a fundamental cycle. So we take the fundamental cycle, this lives in one of the homology groups of this guy, and then we just take that as an invariant. So M, the fundamental class of M, will live in HD of CP infinity Z. And luckily we learned in school what is the homology of CP infinity. In every other dimension it's 0, and in all the others it's Z. So this is 0 if D is odd, and Z if D is even. So when you take this class, you can turn it into a number by seeing how many times, you know, what's the multiple of it with respect to the chosen orientation. If, you know, this is isomorphic to Z, so you might have a little sign issue, but forget about the sign. Does that make sense? Of course, there is this little problem that you might end up with this D to predict that you live in the case when these are all 0, and that's very sad. This is a very good invariant, but it measures nothing. So how can we predict the parity of this D? And so here is a little exercise. So D is congruent to 1 minus B1 plus B2 plus mod 2. Why did I write minus? I have no idea. You know, it's mod 2, so it doesn't matter. But so if pi 1 of x is simply is 1, then this value, which, well, I didn't denote it anything, so Seiberg-Witten of x on the spin C structure x, which is the multiple of M in HD, CP infinity, Z, isomorphic to Z, what do I want to say? Is always 0 once B2 plus is even. So somehow taking this very complicated road, half of the simply connected 4 manifolds, when D2 plus is even, is sort of excluded. This is bad news. Of course, there are ways to out of this catch. For example, you can consider the real Seiberg-Witten invariant. I should emphasize that the real Seiberg-Witten is not against like fake Seiberg-Wittens. Like I'm doing this fake and they do it real. It's probably it will be clear how the real adjective comes along, but you know, just to defend our So when B2 plus is odd, then this becomes an even number. So the groups where my fundamental class lands have some content, and we can talk about these invariants. If B2 plus is even, then this approach is not so great. But we will sort of remedy that at some moment. Okay, so the aim, what we would like to do is find constructions of smooth four manifolds so that we can sort of compute, or what is the, we can control their homeomorphism type and the Seiberg-Witten invariance. And if we have sufficiently many such examples, we hope to be able to show that they are, say, all homeomorphic, but they are not diffeomorphic because we know how to control the Seiberg-Witten invariance, and this is the goal. And I hope I convince you that following the homeotype is sort of, basic algebraic topology. You have to understand how the Euler characteristic and the signature changes, maybe get some knowledge about the parity. And regarding the Seiberg-Witten invariance, well, this is a longer story, but I hope I will convince you that it's not something completely impossible. So there are 2 or 3 constructions, depending on time, I would like to give you today. The first one is the most spectacular, so not surgery. So the input is always a four manifold, as always, closed, connected, oriented, and so on, a torus inside, two-dimensional torus, with trivial normal bundle, which just means that you sort of can push the torus off of itself within its homology class, so there is an isotopic copy just next to it, and a knot K in S3. Okay, so these are the inputs, and now we construct a manifold XK, which will be a very simple matter. We just take X minus an open tubular neighborhood of the torus. Notice that this looks like topologically like D2 cross T2, where I put a little circle indicating that I take the open disk cross T2. This is just the normal bundle, and this is a trivial normal bundle, so that's possible. And in this way, I get a four manifold which now has boundary. The boundary is the same as the boundary of this guy inside T3, inside X, which is just the 3 torus. And we just glue it to another four manifold which has the same boundary. And that will be S3 minus a little open tubular neighborhood of the knot. This is a 3 manifold which has now boundary, the 2 torus, and then I multiply it with S1. And we just glue them together along these T3 boundaries where we have very little restriction on phi, where phi identifies a normal circle of T with longitude of K. So I wrote XK, but this is sort of a little bit of a cheating, right? Because somehow I didn't capture the dependence on phi. There might be a dependence. There are many such phis, and I just pick one, And that's my xk. And so here is the theorem. So this goes back to Princeton and Stern. So suppose that SW of x is not identically 0. So our assumption is that there is at least one spin C structure. For that, this long story I just outlined gives you a number which is not 0. It's simply connected, and even the complement of the torus is simply connected. So this portion is simply connected. Let K1, K2, Kn be an infinite collection of knots so that they have distinct Alexander polynomials. By which I mean that, you know, all the Alexander polynomials are different. So if you take two of these set, then they have distinct Alexander polynomials. Then the xki's are all homeomorphic, but pairwise non-diffeomorphic. Of course, I forgot to put one more condition. B2 plus should be bigger than 1. Okay? So this is sort of quite a general theorem. If you have one example which satisfies these algebraic topological assumptions, and this one, and has the non-trivial Seiberg-Witten invariant, and contains such a torus, then you can create a lot of homeomorphic, non-diffeomorphic manifolds, provided you have such a collection of knots, which is very easy to come up. So you just take these, the usual thing is just to take twist knots, and they will just do the job. Okay, so this is like Kn. It needs a little bit of a thinking to come up with the Alexander polynomial of these guys, and it's not a complicated question. Well, we don't know. The whole, so you can take K and the mirror of K, and those might be diffeomorphic, and other than that, we don't know. You get two manifolds you would like to distinguish, and their Seiberg-Witten invariants are the same. And the only tool you have to distinguish are Seiberg-Witten invariants, so you have no idea. The conjecture is that they are not. That would send the message that even within one homeomorphism type, four-manifold theory is as complicated as knot theory. For knot theorists, that means something. For the rest of us, yeah, well. And I should emphasize that there are other constructions, and I will give you other constructions, so there might be more than knot theory. Question? So this is all you take. So this is the property you need, and then you can compute the Seiberg-Witten invariants. And if you take two different gluings, the Seiberg-Witten theory will not distinguish those. So it might happen that for every knot, there is an infinite family parameterized by different gluings. Well, we have no idea how to distinguish them. Okay. I don't know what that means. No, it has to be, so T should be essential in homology. That's true, but that sort of follows from that condition. This is what you mean? Okay. Yeah. So, no. Let me give you an example when these conditions are met. Say it again. Yeah. It's listed, no? By a junction formula, it will be 0, but no. Yeah. I have a very short answer. So here is an example, or a family of examples. If X is symplectic, so there is a 2 form, which is closed, and omega wedge omega is a volume form. So this is some geometric input. This is a special property of a 4-manifold. And T has a dual sphere, say, i.e. there is an immersion of S2 into X such that immersion I S2 intersection T is 1 point, and B2 plus of X is 1, pi 1 is 1, then the theorem applies. Somehow, this condition will help us to make sure that the complement will have the complement is simply connected, and the symplectic property helps us to check that this seemingly very complicated PDE-related condition holds. And symplectic manifolds are abundant among 4 manifolds we know today. B2 plus is bigger than 1. Where is it? Oh, I see. You are not supposed to put too many conditions, because then you screw them up and then you go. Okay, so so that gives you a lot of possibilities. Notice that the symplectic condition immediately implies that 1 minus B1 plus B2 plus is even. In particular, if it's simply connected, then B2 plus will be always odd. I assume that it's bigger than 1. So it doesn't really tell you anything about 4 manifolds where the B2 plus invariant is even. I think my time is up. So I promised you 3 constructions. I gave you 1. So we will start the next lecture by giving 2 more, and then we'll go to a regime where somehow this condition fails to hold. And it turns out that by giving up a little bit, giving up the fundamental group condition, you can still create interesting 4 manifolds. So that will be the topic. And then Zoltán turned to the first part of the title of the series, Lefschetz fibrations. Any questions? Then, yes? Oh, well, that's a little yoga. So it turns out that symplectic implies that the manifold has an almost complex structure. And then you have the same story as before with the C1 squared. It's a little bit of a computation, but at least it's true. Okay. But I'm done.